Okay, cool.
Okay.
Take it away, Niko.
All right. Thank you very much for the introduction. So yeah, I'm going to talk about this paper, which comes out of a family of papers from the lambda Prolog, I don't know, what's the right word for it, series of papers. I found it a particularly concrete and good one, but I'm going to kind of not go over exactly how the paper presents things, but more try to give the intuition for what it's talking about. So I'll probably be drawing on some other parts from other papers as well. And how I got into this whole area is that I've been working on this kind of formalization and reimplementation of Rust's what we call our trait system, which is kind of like Haskell's type classes, and it's part of our type system. And I'm doing it by essentially lowering it into lambda Prolog, an extended version of lambda Prolog. I call that project Chalk. It's on GitHub. It's now kind of being integrated into the compiler, but I won't talk about it in a lot of detail. So before I go into this too much, I want to first of all just encourage everyone. I've never given these slides. I don't know. They could be good. They could be bad. They're probably confusing. So if you get confused, interrupt me, please. But I'll start out with the basic idea of Prolog. I mean, how many people here have actually used Prolog in some way? Okay, that's a surprisingly large number. So the basic idea is that you define these sort of clauses. They're kind of telling you what's true and what you can prove to be true. Right? And the most basic kind of clause is like these here, where you kind of say, okay, there's a parent relationship and say Zeus is the parent of Athena, right? And they have no conditions. That's just a fact. And in fact, we call those facts. But those are kind of a special case. Those are clauses with no conditions. The more general case is a rule like this, which is saying, for example, these are two rules defining how one can be an ancestor of someone else. Right? So the first one says, somebody A is an ancestor of somebody B if they're a parent of that person. And that makes sense. That's kind of the base case. And then you have this recursive case, which is showing the kind of, or A has a parent B and B has an ancestor C. So you get the transitive closure, right? So all the way up the descendant chain. And you can see this kind of naming convention in Prolog. So lowercase letters are like atoms or facts, and uppercase letters are variables that can be mapped as the program executes. So this rule is saying this A here basically is implicitly a variable scoped to the clause, and every occurrence of A has to be the same. So if you see A 3 times, that's the same person. And these lowercase letters, again, those are just strings that match just by equality. Okay, so this little program, these clauses would define what's true and what we can prove to be true, we can build on. And then you can ask queries or execute goals. And these are things that you will then try to prove using the clauses. Right? So for example, you could say, find me some values of P that are ancestors of Athena. Right? And Prolog will go off and find you one by one all the ancestors. So it'll actually present them one and say, do you want another one? And then you say yes, and then it keeps looking. So Zeus, Kronos, Rhea, all of them, right? And it's good that it asks you, because as it happens, these are Turing complete programs in the end. They can loop forever. So sometimes it never stops. A lot of times you only want the first answer though, and that's okay. You just want to know, is there an answer or not? Anyway, so that's the basic idea of Prolog, right? And what I want to talk about before I actually get into anything in the paper is to kind of cover and explain how a Prolog implementation actually works. Because when you learn Prolog, a lot of times people teach it like I just did, sort of as if it was logic. And that's a recipe, if you've actually written a Prolog program, for disaster, for having your program never finish and never conclude anything, because it's not really logic, or it is, sort of, but the computer is not really that smart, right? It just tries to solve these things in a very rote, simplistic way. So let's walk through it a little bit. So if we had this query, find what are the ancestors P of Athena, and we have down here, these are the kind of clauses that we wrote out. The way Prolog would approach this is it says, well, I know how to prove some things. I have these clauses at the bottom. Let me just try them one by one and see if any of them should happen to work, right? And we can kind of rule out the parent ones because they're proving the wrong thing. We're trying to prove ancestor and they prove parent. But we could start with this one and say, well, to prove, if we apply this here, we kind of substitute, we can match up and say, okay, A has to be P and B has to be Athena, and we get this rule that in order to find an ancestor P of Athena, we can try to prove now some parent of Athena. And to do that, well, we have these other clauses, so we can start going through them. And as it happens, for example, this first one applies. So long as we now take a value. So you see the variable P started out as some person P, but in order to use this clause, we had to make them equal, which means we had to unify P with Athena, or with Zeus, sorry. So you see on the right-hand side, I'm kind of accumulating what are the values each of my variables had to have so far. Started out with no value, now it has Zeus. And at this point, we're actually done because there's nothing left to prove. We had to prove ancestor, or we had to prove parent, we proved parent, there were no further conditions. So we produce an answer. And the way we do that is we take the original question, ancestor P Athena, and we substitute in all the unifications that we found. And then we get an answer, which is kind of the original clause, but with things specified. So we have the answer, Zeus is an ancestor of Athena. Okay. But we're not done. That was the first answer. But if the user wants more, then we can go and keep looking for other rules. So we have this rule here, the second one. And when we apply that rule, we get some new sub-goals. First, we have to prove parent. And then when we're done with that, we have to prove ancestor again. And so we can kind of recursively process these, right? So now we have to prove, our goal was to prove that parent PQ, or what am I saying? Yeah, our goal was to prove, right, parent PQ. And we have a rule, parent Zeus Athena. So we can do that, but we unify both P and Q in the process. And then we would have to go on, because now we found a possible value for P and Q. It satisfies the parent relation. We would go check, does it now satisfy the ancestor relation or not? And as it happens, this one won't. If you kind of work it through, you'll wind up having to prove that Athena is her own parent, and that's not, well, it probably is possible in the Greek myths, but it doesn't actually, in this case, didn't happen. So you can see this is sort of, you can kind of see it's searching through the clauses, right? Finding all the things, all the different ways that, and trying to find a successful path where everything gets proven. So this basic process is called backward chaining. And the idea is you start with the thing you want to prove, and you work backwards from there to try to figure out all the ways that you could have proved it. Yep.
So how does it know if you stop trying to prove it as your own? So one possible is that from parent. That was easy, it shows. But then what if Athena's ancestor of someone is her parent? Like I can look at it and say that's not possible. But
the way it knows how to stop, so I kind of skimmed over that, you're right. But so with first, it'll try to prove that Athena is her own ancestor. And the first rule it can use to do that is to prove that she's her own parent. And there's only 3 rules that allow you to prove parent, and none of them match. So that's ruled out. Then we go to the next rule. And the first thing we have to prove is the parent of Athena is who? Because we know A is known to us. It's Athena. And there is no Athena, there is no parent relation with Athena on the left-hand side. If you look here, she didn't have any children. However, it's a good question, because if in the second rule, I had reordered the 2 clauses, even though that's logically equivalent, it would loop forever. So you don't do that. And this is like the classic example of how to write a bad Prolog program. So yeah, you have to be careful with that.
So there's no cut it out?
There's no, well, there is a Prolog operator called cut, but I'm not talking about it today. But there are other ways. So I'm talking only about the way, there's the way that Prolog is solving this, there's a specific algorithm, I think it's called SLD, and that's what I'm presenting, and it has these pros and cons. There are other search algorithms. So if any of you have heard of mini-canren, for example, or some of these other logic programs, they take a different approach with like a breadth-first search instead of a depth-first search. I'll show why I say that. And they would find solutions in some cases, even if you reordered things. And there's also things called tabling and so on. But the basic Prolog, it'll loop forever here. Yeah. So, right, so this is the backwards chaining, and the basic idea is you can kind of see we had these three components. We had these program clauses, that was the initial thing the programmer gave us, the goals, a kind of stack of goals we were trying to prove, and the unifications that we found so far. And so we can start to define this a little mathematically, how this machine works, right? It's kind of a tuple, where the program clauses we're going to represent by this letter D for definite clause. I'll come back to that later. And the goals are a set of goals, G. And the idea is we have to prove everything in this set. And if the set gets to empty, then we're done. We've successfully found some solution. And the unifications we're going to call theta. And that's just the mapping I was showing you before. Right? And that's our tuple. And so that's a single machine state. And then we can define transitions between these states. And that's kind of how the search proceeds. So let me give you an example. If we started out, our very beginning was we were looking for the ancestor P of Athena. That's kind of our initial state. We have the program, we have no unifications yet, and we have this variable. And each of these things maps up here, right? Then we can transition by applying, say, that first rule, that parent rule. We would just transition like this. We took out an ancestor because now we have some way to prove ancestor, and we substitute in the right-hand side. That's one way we could do it. But it's a non-deterministic machine. We have two choices, actually. There are two transition rules to find. The other possible rule is we could have used the other program clause, in which case we would now have two goals to prove, parent and ancestor. And technically, I guess the way the machine, I don't know, you could define it in different ways, but the ordering would be undefined. But as I said, in actual Prolog, there's a strict ordering here. You have to start with the first one, because otherwise people wouldn't be able to write programs that actually terminate. So essentially, when you have choices, like which program clause to use, these turn into branches in the search space. For any given machine state, we've kind of chosen a branch. And in a real implementation, this defines a graph, and we do a depth-first search over that graph. That's kind of what it is. And the reason they do a depth-first search is that you can implement it really efficiently. You just need a stack. And this unifications table is represented as a Tarzan's union find kind of algorithm. It's very fast, if you're familiar with that. But I won't go into it. But so there was one part of that machine that I didn't clarify very well, which is this thing called which is this letter D. I just said it's a definite clause. It turns out these are called horn clauses, and they have a well-defined logical meaning that I don't really understand. Well, they're first-order logic, basically. And you can define them in a variety of ways, but I'm going to use this grammar to kind of show you how they're structured. So a definite clause, one of those clauses, program clauses, can be any of these letters. I'll come back to them in a second. But you'll notice the second one, well, the first one, A, that just means a fact. A is for an atom. That's like something that's true, like parent Zeus Athena, that's an atom. And then the second one, there's an atom, and this colon dash is kind of if the goals, right? And that's the letter G. And the letter G is the things we have to prove. And they have a slightly different structure. So a goal could be an atom, or it could be ands, and so on. And now you can kind of see how this maps. I'm switching from words to emojis because they fit better and they look nicer. So like the first one is Zeus has a thunderbolt. So that's an atom, right? And it's also a clause. In Prolog, you'd put a dot. And then the second one, here you have someone is scary. X is scary if X has a thunderbolt. And that is actually kind of a compound structure, right? So first we have this for all. That's the variable X is actually bound around the whole clause. So for every X, then inside of it, there would be the implication scary X if thunderbolt X, and each of those is like goals and atoms and so on. So is that pretty clear? Yeah.
So on these two tables here, you've got and in both of them, but you only have or in one of them. Is there an intuition for why I can have goals that say something or something, but I can't have facts which say either something or something?
It's a good question. In fact, well, not the next slide, but in a couple slides, I will answer that question. So let's look at these goals a little bit. They're broken up in this way for a reason. This, in particular, this atom goal thing is separated out because atoms are processed kind of, the user defines how atoms can be proven by writing program clauses. But the rest of this these ands and ors and there exists, those are built into the interpreter itself. And so we can kind of just write these rules. I'll use symbolic notation. But so if you have, for example, if I have to prove G1 and G2, that's one goal, like a compound goal, I can do that by breaking it into two goals that I both must be proven. That's easy. If I have to prove G1 or G2, I can do that. I just have to pick one of them to prove. And it's a non-deterministic choice again, right? Whichever one I want. And you notice this looks a little familiar. This is like the same as when we were solving program clauses and we had a choice to make. So there's kind of a mapping. And in fact, here, there's actually, I don't think there's a Prolog built-in syntax for there exists. Usually it's like a built-in intrinsic predicate or something. But it's a very similar process. If you want to find out if there exists a t such that g is provable, you substitute, you make a fresh variable that doesn't exist anywhere else, let's call it x, and replace every usage of t with x in the goal, and then you just try to prove it. Because that's basically solving there exists problems is like what Prolog's all about, right? So this is kind of exactly the same as when you want to apply a for all program clause. You take like for all x, I think I have an example. Well, that was me working through what substitution does. So if you had a there exists a g such that lightning bolt g, then you just kind of say, well, lightning bolt y for some y. Right, but this is the same as if I had a for all program clause. Because here I'm saying for every g, I can prove it this way. And when I want to apply that clause, I kind of find some specific g that I'm talking about right now. So there's this weird inverse mapping here, right? Proving or goals was the same as and clauses. And proving there exists goals was the same as for all clauses, because clauses are like things you know and things you want to prove, and they get inverted, right? But, oh well, and the atoms are kind of matching up. But as you can see, as the question was, there's no pair for the and goal. There's no for all, no equivalent on the clause side. And what that would mean is kind of, if you did have it, it would be like saying, I know that that either foo or bar is true, but I don't know which one is true. I just know that at least one of them is true. And so that's not, you could make use of that, but it would interfere with this very simple machine that's so beautiful that we've been defining, because now we can't just break up a compound goal into two parts, like the and. Right now we can break an and into two parts, but if we had this thing, we couldn't do that because we can't prove either G1 or G2. We can only prove their combination to be true. And so that would be annoying, so we don't support it. It's also not that useful, typically. So this is why Prolog is awesome, because you have this pretty cool logical language, a really simple solver that you can implement actually quite efficiently. And yet it's actually sound and complete in the sense of if it terminates, the solver is going to find every possible answer to your query, right? But there's like this caveat there, if it terminates. But still, it's very cool. Unfortunately, there are some limitations that are problematic, and that's, now I'm finally getting to the paper. So what this paper is about is how to extend the language of Prolog to support richer queries. And what's kind of cool, and why I could afford to burn half the talk without even getting to the paper, is that it's really easy to do, it turns out, at least these particular extensions. So one of the limitations that Prolog has is that you're always working with these concrete atoms, right? So I can say, for example, find me a G that's a thunderbolt, and it will go find many examples of gods, right? But I can't say something like, for all gods that exist, do they have thunderbolts or not? For all gods that could exist. Can't really ask that, right? And let's be clear about what we mean when we ask that. If we were asking that, we could mean different things. We might mean we have a complete list of gods, iterate over all of them and check if each of them has a thunderbolt. That we could do in Prolog, you can model that. But that's not what we really want to say. What we want to say is more like, for all gods that exist now or in the future, like, is this something I can prove for all things G? And so just having a list like Zeus, that's not enough. But if we had a rule like this, that said thunderbolt for any G, that would be provable. That would be clearly for all G, we can prove it because right there, it's a fact. Okay, so that's the first thing. And then the second thing is we always have in Prolog this fixed set of facts and rules. We might like to be able to add some hypotheses like, well, what if we assume that C is true? Then can we prove G, right? And another way to say it would be like C implies G, right? And that's really useful, especially with for alls, because you might like to say, for all the gods, if they have lightning, then they're scary. That's a general rule, sort of like I am a man. I don't know, something Socrates said, but therefore whatever. But these are really useful things to be able to say in general, and especially as it happens in programming languages that have generics like Rust. But so we'll come back to that. So again, what we mean here is not like for all the things I can see, this is true. And so it wouldn't be enough to say Thunderbolt Zeus, scary Zeus or whatever, and prove the connection. That's like the kind of logic we use actually in real life, but it's pretty fallacious, right? All the ones I can think of, it's true, so therefore it's true. What we really mean is there's some general rule that says like, whenever you're scary, you have a lightning bolt or whichever. And it would also be enough, of course, we don't have to use the hypothesis. So it would be okay to say all gods are scary. That's probably kind of true. Either one would allow us to prove this, right? And yeah, so this is where, as I said, this is pretty useful in a language like Rust. And part of what got me into this whole thing, because if you don't know Rust syntax, it's okay. It's a very simple example, but here we have like a generic function foo defined over some type t, and we want to specify that t is, all we know about t is that it's ordered, that we can compare it. And we know inside we have like a equals b, and we know that that's okay as long as this EQ trait is satisfied. So we can kind of model that as a kind of Prolog predicate. That EQ is a predicate that has to be defined over two t's. And then that turns into this for all if. Right? And for all t, if we know that t ordered, then can we show that t EQ? So you can map these quite nicely. So this, if we try to add this to horn clauses, we get this hereditary Harrop clauses. And while researching this talk, I looked for what the heck this name comes from. And first I found this. I have like a theorem, which is that whenever you search for a famous computer scientist, you actually get a footballer or some other sports figure, and it's a little weird. But anyway, no, it's not him. It turns out it comes from somebody else named Ronald Harrop, also invented independently by Helena Rossioa. And basically, I think I assume both of them were kind of studying how can we extend horn clauses, but still keep this relatively simple proving procedure and have it work. And what they came up with was this hereditary Harrop clauses. They kind of look like horn clauses, but they're different. In particular, they have these two for alls and so on. And you get this interesting structure here now, because now these two formulas are mutually recursive, you'll notice. So the clauses D have goals. They say A if goal here. And the goal side, you have if D, then goal. It goes back to D. So there's this structure, and we'll come back to that, I guess. This is how they display it in the paper, by the way, at the bottom, more traditional math-like notation. I'm giving you my kind of Rust-looking chalky notation. So how can we implement that? I'm going to talk about implementing in the reverse order of how I presented it. So we'll start with if, and then I'll show you how we extend the system to support that, and then talk about for all, because it sort of works better that way. And the basic idea for if is really pretty simple. Instead of just having goals, we can extend our state machine to also carry along a list of hypotheses. And these are just clauses like D. They're the same structure as a program clause. So in a way, you could think about a Prolog program that just always starts with an empty set and then implies like the whole program can fit into the goal, essentially, which is cool. So now we can kind of define a simple rule that says, okay, let's walk through this, see how much I defined. Okay, good. We start out with an implies goal. So you see on the left this true. That's kind of like the starting set for our hypotheses, which is nothing, right? It's something that's true always. And we can, we have this goal, this implies goal, we can break it down and move the one hypothesis over into the list of hypotheses. I just made a compound hypothesis here, and then we just have our goal. And now we just proceed like we always did. The only difference is when we want to prove some atom, like in that case, scary God or whatever, in addition to checking the program clauses from the user, we also check the hypotheses. Done. And so, right, so now we see that there's kind of this connection, because the A implies G. Before it was lonely all by its lonesome. It didn't have a pair on the goal, but now it does. These basically work exactly the same in the machine level, more or less. Only difference, if you look at them as in implies notation, you see in the clauses we have goal implies clause, and in the goal we have the clause implies goal. So they change roles. And they do this precisely so as to rule out what you were asking about, to rule out, so you can have the goals have a richer set of options like ands and there exists that don't appear on the other side, because that would make the machine more complicated. So we set up this mutually recursive structure.
Can I ask you just to go back one slide, just to refresh my memory, please? One more. All right.
Okay. My pleasure. Okay, so that's how we get if. Pretty easy. And what about for all? This one's a little more interesting. So the idea is we're going to define these things called universes, and they're basically sets of names. So we start out with this universe, this root universe U0, and it has all the global names that the user typed into their program and all the ones they could possibly type. And then we're going to extend with other universes, and each new universe is going to add one more name. And I'm using this weird notation, bang U1. There's lots of different names for what to call these, but it's basically like a fresh name that's not equal to any of the names that existed before in any of the parent universes. And we can kind of build a little tree of universes, actually. So U0 could have a subuniverse U1, which then gets extended by a new universe U2. And for any one of these universes, like for U2, it can name everything in itself and all of its parents, but it can't name the stuff off in other cousins and siblings or whatever, aunts and uncles. And so now we can, let's see. Now we can kind of start to define how do we process a for all goal. So if we're at the state in the machine where we have a for all goal, basically we make some fresh universe U, the next one, let's say, in our list, and we replace T with this bang U. And now it's some fresh name that we know that the user never used. So the user can't have written a rule that targets it unless they were writing, like that would be an example, unless they were writing a generic rule. Right? So if this was our case, we had to prove Thunderbolt of G. Now we're proving Thunderbolt of bang 1. And so if they had a rule like Thunderbolt of Zeus, that can't work because Zeus will never be equal to bang 1. Right? But something like this would be okay because G is a variable, and G can be any name, including these bang names. Right? Okay, that's almost right. Yeah.
So are we gonna are these used like a resource and like global across the whole solver then, and we're like continuously doing like bang you and bang bang you and bang 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 you? Like what's keeping track of the state?
Yeah, so that's a good question. I want to come to it in another slide actually, because first I want to question. I said here G can be any name, even U1. That's true, but it's not exactly true. It's not the whole story, which is to say, well, what I just gave as an example was kind of like this. We said for all A, there exists an E such that E equals A or A equals E. Right? That's kind of what we wanted to prove, minus all the scaries and gods and bangs. That's the relationship between the names. And that's okay. That's fine, because E can just be A, right? Sort of, or bang U1, depending on your point of view. But what about this one? Is there some E that for all names A, it's equal to E? That shouldn't work, because that E would have to be many different names for that to be true, right? And so the reason that shouldn't be provable, but if we're not careful, if we just did what I said so far, then you would be able to prove that, and that would be wrong. So what we do is we give every existential variable, every variable like E, a universe that it was in when it was created, and it can only name names visible to that universe. So like here, we start out, we're kind of in universe 0 to begin with before we've done anything. And we have some notion of a current universe, kind of. which is getting at your question. And I want to show you how it works in the machine. But let's just assume we have what is the current universe. When we enter into the for all, the current universe changes to U1. And now when we create E, we say, what's the current universe? It's U1. We associate that. And so now when we want to ask whether E can be equal to bang U1, we look at what universe was E defined in, and that's okay, everything works out. Of course, here, E is defined in U0, and U1 is only for that little portion. So when we go to unify A and E, it fails, because E is in the wrong universe, and it can't name U1.
So I noticed you used the word existential earlier. Should I interpret this in the same context as existential types, or is this a different?
It's the same.
Okay.
Yeah, there exists I guess the difference would be usually with an existential type, you have some hidden type that you don't know, but you kind of open it and work with it abstractly. That's kind of what we're doing, but actually more with the for alls in this case. This is more like the same notion of there exists, but not the one that we don't know, but rather there exists a variable and we're going to find out what it is. I get confused about that. There's a lot of relation for all. There seems to be different people who use the same words in slightly different ways.
Why is it that lowercase u1 doesn't cover the outer curly braces?
Oh, wait. Well, is your confusion that I made it end here?
No, that you
Okay,
made it
'cause that-
start.
I see. Okay, so first of all, it shouldn't have ended here. It should have ended here.
Okay.
That was a mistake. But secondly, why does it start? Because it starts essentially when you enter the for all. That's when you make the new universe, and all the things inside the braces of the for all.
Okay, so so for all introduces this, but exists does not.
That's right. And to come back to your existential type question, I think actually the reason for the difference I was pointing out is exactly how I was saying that that exists and for all in the clauses and in the goals are playing like the same role. I think it's exactly that. A normal existential type is actually more like a clause. It's something you can rely on to be true, that there exists a type T. You don't know what it is, right? And here that's exactly what a clause says too, that sort of you can rely on it to be true, that for whatever G you find, if you so that probably explains why. But okay. So now, how do we extend the machine? Well, this is the final machine that they presented in the paper to include this notion of a current universe and track all that data. And you see it's got more letters. So we have the letter we started with, D, and we have this list of hypotheses. We saw that when we added the if in there. And we have the goal that we started with. And then in addition, for every machine thing that we're trying to prove, we're now carrying along, we have the substitution. We always had that. But we're now carrying along this current universe counter, and that's I. And so that's when we, for example, enter a for all, we're actually going to increment this counter, make a new child universe. And then we have this L, that's tracking for every variable. So theta tracks its value, and L tracks what universe it's in, its label. This is one way to implement it. You can do slightly different variations, but this is the basic idea. And there's one interesting property here that I sort of glossed over. It may have caught your ear. I said universe counter, right? And it's true. All we have to do, it turns out, is to have we can represent universes, the whole tree of universes, just by one number, 0, 1, 2, 3, 4, 5. And that's a little surprising because when you look at this tree, it has like shape, more than linear shape. So you might think, for example, if we only track the current universe and we have the value is 3, how do we know that it can't see 2? It shouldn't be able to see 2. The answer is we don't know that, but we don't care, because it turns out we'll never have to ask that question. And the reason, you can kind of see it. Ignore that stuff on the bottom that wasn't supposed to show up already. You can kind of see it if you think, how would it happen that those two universes would interact anyway? They're siblings, so they had to be created by distinct for all statements, kind of like here. We have for all A, and then outside of it, for all B. And how can those two for all statements kind of communicate? The only way they can communicate, there's no return values in Prolog. They communicate by a shared existential variable that they can both talk about. And if you have that, then, what am I trying to say here? Okay, I see. If you have that, then basically here, this is appearing in the wrong order, but the idea is it's going to be in universe 0 in this case, right? Not in any of the universes that they could talk about. So we'll start out here with L equals nothing, and then we'll instantiate E with some fresh variable, which we'll call E again, because it's not used anywhere else. And it's going to be in universe 0. And so now, when we actually, remember, we're going from one goal, which is an and, to 2 goals. So we change to a comma. And then when we try to actually process one of them, like when we enter the for alls, we're now trying to prove that E should be equal to bang U1, but E is in U0. And you can't put bang U1 into a variable that lives in U0. So essentially we're saying the only way they can communicate is to have through some variable that is in neither scope and therefore couldn't take, the only values that E can take on are values that both of those scopes can name anyway, things from universe 0. So that, in fact, we don't have to worry about that problem. And we can just use a counter and say, is A less than B? And that's really efficient. We don't have to like allocate memory to represent the tree or anything like that. Does this make sense? It appeared in all the wrong orders.
Is it always Z0 or is it the current of U1?
It's the mutual parent. In this example, it would always be the immediate parent. It may not be U0 because this may have been part of some bigger clause. But in general, it would have to be some mutual ancestor.
So I have a question for the class group. Is anybody here a type theorist? Or are universes kinds?
Yes. I think that there's an analogy.
Because I am not, obviously.
They would be like, I think Agda or some, I don't really know Agda, but I think that they have a way to extend a kind. You begin with star, it's kind of all the types, and then you can have a new one. And that's like this, same idea. So I don't know if they are kinds, but there's definitely a relationship.
So why did we end up with different, so is the way to read this slide that it's showing sort of the sequence of transformations we're going to do to try to prove the
Yes.
goal? So I don't understand the step from the third version. So we go from, I understand how we go from for all A, something and something else. We sort of convert that into prove both of them,
Mhm.
the comma there. I don't understand why we got E equals bang U1 and E equals bang U2 in the next step.
I think I took a little shortcut there.
Okay.
So there really would be some more than one intermediate step, and actually you probably couldn't get to that state because, so what really would happen is first you would expand the first goal, the for all A, and you'd end up with the E equals bang U1, and then on the right-hand side it would be for all B equals B. That's be the same. In fact, hold on. Oh, this may be why I did it. Now it messes up all my beautiful indentation. Okay, this was possibly an error. Live edit slides. It's fine. Ta-da! Okay, so this is like where actually you would go in one step.
Okay.
And now, at this point, if you try to prove the first goal, you will just fail, and the whole there's no successor kind of.
Why do we get bang U2 instead of U1? Because we decremented the counter.
No, hold on. That was wrong too. We didn't touch this yet. This is just exactly the same.
Okay. And you
Ta-da!
fail at this point. Why?
Because we have to prove E equals bang U1.
Yep.
And E is in universe 0.
Okay.
And 1 is bigger than 0. And therefore, universe 0 cannot see universe 1. And so we fail. We can only prove E equals bang U1 if it's a value that E can actually take on.
Okay.
Yeah. So I don't recall whether you have the freedom. I think this kind of depends. Like in Prolog, you would always prove the first goal first. If you had the freedom to prove the goals in any order, which in theory you do, then you could take another transition and be in the state I was originally showing.
Okay.
Sort of. Yeah.
Just to follow up on that, so there's this idea in logic programming kind of developing algorithm. And so the don't go non-determinism is where you're kind of forced to go in order. So you have to look at the clauses in order or parallel.
Yeah.
And the don't care non-determinism is kind of where you have a little bit of freedom. And so injunctions are one example where you kind of take them apart.
That can't be true. There probably is a way to say a different kind of and where you don't care or whatever. I think you would usually do that with like some cuts and whatever, but I pretend cut doesn't exist. Yeah, potentially, but it doesn't really matter. However you do it, you're going to get eventually into a state where you have some unification you can't successfully do. And so in the paper, there's a little more stuff I didn't talk about. Specifically, like you might wonder, you probably didn't, if you have two existential variables and you unify them and you don't yet, like here I'm showing E equals bang U1. What if I had like there exists an E and there exists an F such that E equals F and F equals bang U1 and so on? That's pretty simple. Basically, all that happens is you always pick the most restrictive label because if E and F have to have the same value, then it must be a value that they can both name. So it must be the earliest universe. As long as you do that accounting, everything kind of just falls out. And you can do this check if you're into union find, my favorite algorithm. You can do this as part of the occurs check. So it's kind of the price you're already paying, basically. It's free. So that's it. Now we just extended Prolog. So if you like this, you could consider joining and helping us rework Rust in this beautiful image. Alternatively, you could just read this book, which is really cool. This is Dale Miller and Gopalan Nadathur's kind of opus, where they cover all of Prolog and all the cool things you can do with it. And they show, for example, how you can use these for alls and ifs to model module systems and do all kinds of neat stuff. But that's where I kind of got into all this from. So thanks.
We've been having plenty of questions throughout. Any other follow-on questions from anyone?
Yep.
So I'm curious, so you touched briefly on how this actually connects back to the work you've been doing on Rust, just sort of proving predicates about relationships between traits. Is that the primary application? Is just like these like implication relationships between traits, or are there other applications? Or like, what are the kinds of facts? Like, you know, the examples you showed here, like the facts that we had were like lightning bolts and scary. What are like the facts that you're interested in Rust, and like what are the relations that you have between types? Yeah,
that's a good question. We're starting out with pretty directly trying to model the trait system, which means that it's not as simple as you might think. It's not just is this trait implemented. There's different varieties. For example, we sometimes distinguish like we basically have a couple of different ways to prove whether something is implemented, and we make differences. So for example, if it came from the where clauses that we saw, we have a special fact to say, I proved it based on one of those where clause bounds versus I proved it from an impl, and that allows you to make different things. But it maps pretty closely nonetheless. I think where we would like to go from here, once we have this all working, is extending this more to cover a lot of the type checker implementation itself. So there are places where we sort of have hand-coded proof search, essentially. So for example, if you might ask, I have some variable, it has a type T, I use it where a type U is expected, can I coerce from T to U? And that's kind of complex to figure out in Rust. Like in many languages, there's like a bunch of different kinds of coercions, and you want to see, do any of them apply? It would be really nicely modeled by a bunch of Prolog rules. And I'm sure as a bonus, it would fix a lot of bugs, right? But we haven't got there yet. And there's some risk there. That's like I kept harping on if it terminates. Well, you have to be a little careful, go piece by piece, because you may end up, a lot of times the hand-coded proof search has these bugs where it doesn't find solutions, but they're kind of features also because they just go a lot faster when you don't look at that part of the search space. So we're going to see kind of what we have to do to model that faithfully, and how faithfully we need to in order to keep it performant.
So I guess kind of related. Once the Rust compiler sort of, or the type checker integrates some of this, would you run into sort of non-termination issues? You just like cut off the search at a certain point?
Yeah, so the actual solving algorithm that I'm currently tinkering with is not this one exactly. It's called SLG. I don't know what that stands for, but it's I'm using a mini Canren inspired version that uses a breadth first search, and I'm doing all of this because of exactly that problem. So we're using some techniques to prevent the guaranteed termination at the cost of completeness, basically. Meaning, so for example, it's very simple. Basically, if a term gets really big, we will just come back and say, we don't know if it's true or not. And the SLG is not just true or false, it has a richer notion. You can also say ambiguous. And you need that sometimes. And that's useful here because we can say, like, we were trying to prove, is this really big type equal to the other really big type? And we just sort of stopped and said maybe, and we let that go back up, you know. But the idea is we prefer not to get to that point because that meant we already had to build this really big type. That's like the fallback. The preferred strategy is actually to use, most of the time in the type checker, we're looking for a unique answer actually. Like in Prolog, you kind of just find some big old thing and it's okay. But we would like to not guess too much on the user's behalf. So we don't want to just pick things out of thin air. We want it to be kind of, there's the only one possible answer we could have done. So by doing the breadth first search, we kind of find the most diverse set of answers as fast as we can. So in other words, instead of exploring like vec of t, vec of vec of t, vec of vec of vec of t, like you would do in Prolog, we'll explore all the types out there. And that way we'll pretty quickly find out if we've got more than one answer or not. That's all we really care, right? So the idea is that we'll stop iterating as soon as we see that we have at least two answers, we're done. Yep.
Well, it's kind of about both. So in like the Haskell type classes, there's kind of the implication part where you have parts that goes. But so what that drives is the construction of like dictionaries of functions.
Yeah.
So it's not just like a true or false answer like you get from Prolog, but it's
right.
There's like something that gets built up. So
Mm-hmm.
modeling that part also.
Yeah, that's a really good question. So we are modeling it. There would be two ways to model it. You could model it. We don't build up dictionaries as it happens, but we still have to answer the same question, which is kind of, not only is it implemented, but when you call that function, what code should I run? Right? That's like the question at hand. And you could do that based on essentially the proof tree. That would tell you. So those rules map to user's code, and that code is kind of, you can label the edges and then you could do it. I'm taking a slightly different approach, which is that in Rust, kind of every method, for example, that you call, every method that you write has its own unique type. It's like a singleton type, only inhabited by one value. And in fact, it's zero size, just kind of a notion. And so if you want to find out, for example, what code should I run when you call this method foo, there's like a relation that says the type t for the trait foo has this type for its method foo. And that's a unique type. There should only be one. It'll come from the impl. And that type just tells us immediately what code to run, basically. So actually, we get to use the more Prolog-y approach where we just want to know the answer. We don't care about the proof tree, which is kind of nice.
So I'd like to go back a slide, please.
Okay.
And it seemed to me, I forget exactly where here, that we were talking about substitution.
Yes. Well, all these steps, the first step and the third step involve substitution at least.
So tell me about Liscov's
Substitution principle?
Yeah, and do we have the concepts of subtyping and covariance, contravariance?
No. It doesn't really apply here because Prolog is all about equals. So we don't really have a notion of subtyping. If you did, you would probably model it as a relation. And it actually does come up in the Rust model, for example. So it's not, instead you would not be saying that these two types must be the same, but rather that subtype TU must be true. And then you can define when that's true. And then you would have to think about covariance and contravariance and all of that, but doesn't enter into base Prolog.
So when you're I guess one question is what kinds of questions are you actually using the Prolog implementation to answer about someone's Rust programs? Like one example is like, where do I find the implementation of all these trait methods? Are there other questions you're asking, like lifetime bounds?
Almost always you're asking, is this implemented or not?
Okay.
So like every time if we jump back, oopsie. Where was my Rust code? There it is. When I call this function foo, I am going to have some value for the type t in mind, and I then have to prove as the caller that it implements ord. And that's a trait proof. That's a goal, a Prolog query.
So if you successfully prove that goal, then you're happy, right? And you pull that out. If you fail to prove that goal, is there useful information you can extract from the Prolog failure to like give a useful error message or something? Like what's the story for failure here?
Yes, there would be. That's actually where the proof tree would be. Not just the proof tree really, but like, well, you don't have a proof tree because you failed. Sure. So, but your failures, the graph you searched but failed to find a complete tree in is pretty useful. We're not doing anything like that yet, but I did have in mind that we would reconstruct an error and we can tell you, for example, well, maybe you thought that impl would apply, but here's why it didn't, because I went down this way and this wasn't there. I don't know if you've used like GCC, but I remember that from years ago when I wrote C++ code, that sometimes you would call something and it would tell you like, here are 10 different overloads, and here's exactly why each one of them didn't apply. And it might be like 20 pages long, but it's really useful when you're trying to figure out why that overload did not apply.
GCC 8 now has like a tree printer.
See, so I envision we could do something like that. Although there's always this balance between like overwhelming people and telling them what they need to know.
Whenever I get this sort of error from GCC, I just don't look and go, okay, what am I forgetting?
And this might be the first time I've heard of somebody taking inspiration from the C++ template.
I like that, not the template errors. No. Just that overload error was useful.
New GCC, actually, they did a whole bunch of work very recently.
But,
So are you with your version?
yes, yeah, to both. Yeah, it's not. We're not. To be clear, we do not yet use the new solver in Rust C, but we are hacking on it as we speak.
That's chalk.
That's chalk. Yeah, it's actually like so the real relationship is that there's this project called Chalk and the Rust C, and then there's a shared project called Chalk Engine that contains the code that they both share. And so Chalk is kind of an elaborate unit testing harness for the engine. Okay. Yeah. One last question, maybe.
What thing where you solves?
That's a good question.
Why?
It's basically the same, except it's totally different. It's I think the right analogy, basically we're solving them today. We solve them well, actually we use a completely different algorithm that's really bad, but the bigger difference is, because I didn't understand how to do this when I first wrote it, but the bigger difference is that we're solving them in terms of Rust directly. Like we say, does this type implement that trait? Whereas the new engine doesn't know anything about Rust. It just knows about the stuff I've been telling you about, right? Atoms are like this opaque thing that it knows how to unify. It's all very generic, which makes it a lot simpler. So it's basically, if you've ever worked on a compiler, or probably any sufficiently complex program, you introduce an IR, a new intermediate representation, and all of a sudden, a program that seemed completely intractable is actually pretty easy because you separate into two parts. First, breaking down your problem and expressing it in terms of this simpler thing, and then solving the simpler problem. And that's what we're going for. So we've separated out, we essentially take in as input a Rust program, compile it to program clauses, to Prolog, kind of, or this extended variant of Prolog, and then execute that with the engine.
Okay. Thanks again to Niko.
Thanks, everyone.